So in the previous video where we introduced Hooke's law, we said that the tension was equal to K, the stiffness in the string, times X, the extension of the string. Okay? In a very kind of like base case scenario, if you had a particle, it might be a box, being pulled along horizontally, it's attached to a wall, and then it goes past its point where the string is taut, then what we're considering is the tension in the string working against the direction of motion, and we can use F is equal to ma to say, well, the net force here would be horizontally would be minus t, so minus kx is equal to m, the mass of the particle, times the acceleration, which is d2x by dt squared. So this gives you like a very base case differential equation to work with. Okay. Now you can also have situations where you'll have a damping force acting in the opposite direction to the velocity of the particle. Now what I mean by that is that if you just have this situation, you're going to get simple harmonic motion. Okay, there's nothing stopping this, so what all it will be would be the elasticity in the string, that when you pull it that way, it's just going to and it's going to keep on going on and on like that forever. Okay, so that's what you would end up finding. And likewise, if you had a situation where you've got a box being pulled downwards, okay, likewise, you can have that moving up and down, okay, in the same way. So we could add a damping force to this, where we could have a force that's working against the direction of motion. It could be air resistance, for example, okay, which is a multiple of the velocity of the particle. So it could be k times x dot, for example, so dx by dt. Now you can include that with the tension, but if we just look at a base case scenario, we would have the net force. So if we just consider that one there, is equal to the mass times the acceleration. Okay, where k is just another constant here. You know, I could call that another letter if you like. Let's call that p. Okay, and so you get this type of scenario. So what you'll get there are situations where you're going to have an air resistance force, meaning that this won't bounce up and down continually forever and ever and ever. What it will do, well, it will keep on bouncing, but what it will do is it will slow down. You'll get that e to the minus t part, okay, or e to the minus kt part coming through from your differential equation, which will cause damped oscillations. Okay, so it will and it will slow down. Okay, so you can have these situations where you can also have your tension from that. So you could have, for example, minus kx take away p dx by dt is equal to m d2x by dt squared. Okay, for example. So here is your net force is equal to mass times acceleration. You could also have the weight of the particle added in. Okay, so that could be m times g, and so you then have mg going downwards, take away the tension, take away the force that you've got there, which could be your air resistance, so proportional to the velocity of the particle, is equal to mass times acceleration. So these are the types of problems that you can build up, and it goes to and leads towards solving second order differential equations in the way that we have met.